Welcome everyone. I am making this thing that we have been discussing on the ensembles. Okay, these are the classifications of ensembles. The first is called microcanonical ensemble, the second is called canonical ensemble, and the third one is called grand canonical ensemble. Therefore, let's start with the microcanonical ensemble. I am giving an outline of this thing and will be discussed on each topic will be discussed with a single video. Okay, micro, first let's write canonical ensemble. This is the first ensemble we will be discussing on. Okay, this is what an ensemble. You can write this thing out. In which a microstate is defined as NVE. Okay, a microstate is defined as NVE. Therefore, what does this signify? That number of particles will not be changed. Number of particles will not be changed. Volume will not be changed. Okay, and the same thing, the energy will not be. This is the NVE structure, or in case of microcanonical ensemble, you can write it like this. In microcanonical ensemble, the NVE structure does not change. Therefore, the mental copies have say this is the original copy. Say this is the original copy. What we have learned on the ensemble, that this is the original copy, and we used to take the Xerox copies of this thing out. Okay. Therefore, these are the mental copies. These are the mental copies. Okay. In this thing, the number of particles, volume, energy will be copied on this thing also, NVE, and also in this thing NVE, and so on and so on. These things will not be changed. To make this thing, the walls of the system, say this is a box. Say this is a box. In this box, there are some particles at some temperature, at some energy, at some volume. Okay, this is in some NVE written. So what we can see from this thing, that if n is constant, that means the walls are impermeable. What does it mean by the impermeable walls? Impermeable walls means the wall will resist for incoming particles and outgoing particles. That means no particle can go outside the box, or no particle can come inside the box. Okay, this is the impermeable box concept. Okay, or sometimes it is called impenetrable. Impenetrable. This means the particle doesn't, the box does not have any pore on its sides. Okay, the pore on it is a sealed box. Say it is a sealed box. Okay. Now the volume constant means what? This means wall of the system is rigid. Rigid wall means you cannot press the walls by pushing towards inside. Okay, you cannot press the walls. It will not goes, it will not bend like this. The wall does not bend like this. Okay, this, if this happens, then volume will be decreased, but the walls are rigid. This means you can compare it with your wall of your room. Okay, the rooms are, say, it is not 100%, but it is mostly, this is a rigid wall. Therefore, by pushing a wall, you cannot move a wall. Okay, this is the concept of what volume constant is. And the energy constant means energy constant means the walls are adiabatic. Adiabatic means, sometimes when I was in college, I used to call this thing a diabetic. Okay, this is not diabetes, this is not linked with diabetes. Okay, I used to call this thing out for fun. Okay, walls are adiabatic. Adiabatic means no heat can enter the system. No heat can enter the system. This means no heat can enter the system, or no heat can goes out of the system. Okay, this is called a adiabatic wall. Okay, so the type of the wall becomes finally for microcanonical ensemble. Okay, microcanonical ensemble, the wall is what, for to make n constant, the to make n constant, the wall becomes um, impermeable. To make volume constant, the wall has to be rigid. To make energy constant, energy means heat energy, you can compare it with heat energy. Okay, any source of energy could not enter the system, or can go out of the system. Okay, this means the wall has to be adiabatic. A diabatic. Okay, impermeable, rigid and diabatic wall makes a microcanonical ensemble. Okay, system, you can write this thing out. Okay, the system is what, therefore the system will be isolated. A isolated system is what, isolated system, that means no other system are in the surrounding of the particular system. Because if your system, say this is our system, this is NVE, our microcanonical ensemble, it is in touch with another system, then it will try to enter this system. Okay, or it will push the wall. Okay, or the particles of this thing want to go inside the subjected, inside this subjected microcanonical ensemble. Therefore the system has to be isolated, like an island. Okay, like an island. Say this is an island, say this is an island. Okay, say this is an island. Okay, and these are the sea. This is the sea. Say this is, this is Arabian Sea. Okay, this means no one can enter the island, or no one can go outside the island. This is the one and only island. You can see the one and only island in the world. Okay, this means no one can get rid of the island, or no one can enter the island. This is a artist preview of microcanonical ensemble. Next, go to the canonical ensemble. canonical ensemble. Okay, wait for a while. Canonical ensemble. In case of canonical ensemble, there are three things which are constant. Okay, the number of particles, the volume, and the temperature is constant. In case of microcanonical ensemble, what we have seen that there are number of particles, volume, and the total energy of the system remains constant. In case of canonical ensemble, the number of particles, volume, and temperature remains constant. To make this thing out, this is the system is can be drawn like this. This is NVT. This is the original system, and these are the mental copies. Okay, these are the mental copies. This is same system, same the Xerox copies. These are the mental copies. In this thing also NVT is constant. NVT is constant. Okay, to make NVT constant, NVT constant. To make NVT constant, first of all, to make N constant, write N constant, the wall has to be, the wall of the system has to be impermeable. Okay, this is similar to the previous topic. Okay, wall has to be impermeable. To make V constant here, the wall has to be rigid walls. Okay, now it comes to the third point that where it changes. Okay, is to make NT constant. This means the wall has to be diathermic. Okay, this means and also, okay, let me write it. Let's understand this thing. Let's say this is the system. Say this is the system. To make N constant, the wall has to be impermeable. Okay, impermeable means no particle can go outside the box or no particle can come inside the box. Okay, this thing is okay, and wall has to be rigid walls to make the volume constant. This means no one can squeeze the wall of the system. Okay, and to make T constant, that means the temperature inside the system constant. The heat has to be go out of the box, and the heat also can have to be enter a system. Okay, this means say the system was initially in 32 degrees centigrade, and the system by some means the system increases its temperature, so it has to cool down. To become cool down, what it has to do, it has to release some heat from this thing. Okay, to make this thing, the wall has to be diathermic. A diathermic wall means the wall from which heat can goes out or can come in. Okay, this is, say this system was initially, this is initial, the system was initially in 32 degrees centigrade, and by some means the system becomes 31 degrees centigrade. That the external heat has to enter the system to heat this system up. Okay, now the question arises, from where the external heat will be produced. Okay, from where the external heat will be produced. So the system Here comes a concept called heat bath. Heat bath. To make this thing out, the system has to be maintained in contact with an infinite heat bath. Okay, this is the line to be focused on. This is the line, infinite heat bath. Infinite heat bath. Say this is, I'm elaborating this thing out. Say this is our system in which N, V, and T has to be constant. Okay. So this green thing is an infinite heat bath. Okay. This is an infinite heat bath. Sorry, this I had this color. So this is an infinite heat bath. Okay, what is this? It is infinite heat bath. Let me write it. Infinite heat bath. When the system cools down, the heat will enter from this infinite heat bath. Heat bath gives heat when it is needed, and heat bath also takes heat when the system becomes heated. Okay, this thing, when heat needed, this means when heat is needed, and this thing means when heat has to be drawn out. So in the example, I have told you one thing, that when the system cools down, this means it needs some heat to maintain its particular temperature. Therefore, infinite heat bath will give the external heat to heat up the system, and um, and when the system heated up by some means, the infinite heat bath will take the excess heat from the system to make the system cool down and to maintain a particular temperature T. Okay, say in case of in uh, in cold days, okay, in winters, uh, when we feel cool, then we used to keep in touch with a heat object. This means this is the infinite, this is the heat. You can say this is a heat bath. Okay, this is fire. Say this is fire, and this is some person. Okay, and when the in say this person is in minus 20 degrees centigrade, this is very cold. He is in Siberia, and he had to maintain his body temperature, a particular temperature. Okay, say our body temperature 98 in degree centigrade. I don't know in degree what is in degree centigrade. Okay, say this is 40 degrees centigrade. Sorry, say this is 40 degrees centigrade, and we have to take some heat to maintain our body temperature, and the fire gives us this thing. And in case of say, in case of this is winter. Okay, this is winter, this is summer. In this next, okay, this is summer. In summer, we take say ice bath. We take ice bath. Some of the people take ice bath. I don't take usually. Okay, so this is ice bath, and this is fire. I like to draw this thing. Okay, this is ice bath. So when you feel hot, okay, when you feel hot, okay, what you do, you jump into the ice bath, and the ice bath tries to maintain your body temperature, which is lower than the atmospheric temperature. Okay, this is the work of infinite heat bath. Infinite heat bath do both of the things. Okay, this is, and the system, in this case the system is called, system is called a closed system, closed but not isolated. You can see this thing out, that the system is closed. Okay, this is, the system is closed because the walls are rigid but not isolated. Okay, in the previous case we have discussed a island type example. Okay, this is in the case of the island will be in touch of another island. Okay, you can conclude this thing out. This is the canonical ensemble. Okay, now grand canonical ensemble is what. Now grand canonical ensemble, this one is the last ensemble we'll be discussing on. And see, these are the outlines of, or the concepts we'll be discussing with more elaborate relation. Okay, what is grand canonical ensemble? Grand canonical ensemble means mu vt are constant. What is mu? Where mu is a new parameter to you. Mu is called chemical potential. Okay, chemical potential. You can resemble this thing with the energy. This is a kind of energy, potential energy, energy released in, released not in, released during. You can write this thing, right? During, energy released during a chemical reaction. Okay, when mu is constant, when mu is constant, then the number of particles, the number of particles in a system will be changing. Okay, number of, say this is a system and you have some particle inside this, and this particle goes out and comes in, goes out and comes in, uh, up to which this thing will be continued, the mu remains constant. But if number of particles become constant inside the thing, if number of particles become constant, then mu will be 0. Okay, for a, say for a isolated system, in case of, so what we can see from this thing, in case of microcanonical ensemble and canonical ensemble, the number of particles for a system were constants. For constant number of particles, you can see the number of particles are not changing. That means in the previous two cases mu will be 0, but in this case mu is constant, and this constancy means number of particles will be changing. Okay, so what we have to we have seen from this, the walls, for mu to make constant this thing out, the wall, if there are walls, then the walls has to be permeable or porous. This means the wall contains these are pores. These are pores. Okay, or the system could be a open system. Say a glass of, say a glass of coffee. Okay, a glass of coffee. In a glass of coffee, you can see the number of particles can, these are the vapors. Okay, these are the vapors. the number of particles can go outside this and also can come inside this. Okay, this means this is in this case the mu remains constant, therefore number of particles are changing. Okay. Okay, second term tells us that v is constant. We have seen what to make v is constant. Okay, that the walls are rigid, this means, and to make t constant, the last term was the wall t constant, walls has to be diathermic. Okay, walls has to be diathermic, and to make this thing, the system also, the system, this is mu vt, a grand canonical system has to remain in contact with a infinite heat bath also, because the t should remain constant, and to make t constant, the system should be filled with heat, or the excess heat from the system could go out of the system. Okay, this is the outline discussion of three types of ensembles, and we will be discussing on elaborately about each of the ensembles on upcoming lectures. Okay, now up to this, thank you.